In this video, we will discuss fundamental matrices in the context of initial value problems. Suppose we have an initial value problem. X prime equals ax. X of 0 equals x sub 0. We set up the fundamental matrix of this equation. Phi of t is the matrix whose columns are linearly independent solutions to this equation. And at this point in our mathematical career, we can find these columns using eigenvalues and eigenvectors. Solving this is something we can do. It's only the initial condition that's complicating things. So the general solution, we are not looking at the initial conditions yet, is the linear combination of these columns. A linear combination of column vectors is a matrix times a vector. In particular, this matrix times a vector of coefficients. This matrix is phi. So x equals phi of t times c. To make this satisfy the initial condition, we need to properly select values of c. Now, x of 0 is x sub 0. X of 0 is also phi of 0 times c. So we set them equal to each other. Not every matrix has an inverse, but it is guaranteed. We won't discuss why until linear algebra, that this matrix has an inverse. So we can multiply both sides of this equation by that inverse. On this side, these turn into the identity, and the identity times a vector is just the vector. So phi of 0 inverse times x sub 0 equals this coefficient vector c. Take this and plug it into there to get an equation for x. X equals phi of t times phi of 0 inverse times x sub 0. Note that phi of t is a matrix of functions, while phi of 0 is a numerical matrix. This is not the inverse of phi of t, and these do not cancel into the identity matrix. In this video, we've seen how we can use fundamental matrices to solve initial conditions. We observe that it is also possible to do this simply using Gaussian elimination. We'll discuss this when we look at an example.